Well, good morning, everyone. Good morning, everyone. God, want to make sure everybody's awake. Um, just maybe by a show of hands, I mean, how many here are involved in atmosphere heat treating that involves carburizing, carbonitriding, nitriding, etc.? Gee, what a surprise. Um, how about vacuum carburizing or vacuum carbonitriding or something? And obviously, how about both? I mean, there's people in the audience, I'm sure, that get involved in both. Um, well, what I'd like to do over the next few minutes is to talk about various lessons learned in the subject of case hardening in general. This is a broad subject, hard to cover all aspects of it, but I'll certainly give it a shot as to come up with a few things. I want to start off by really acknowledging one individual in particular, a fellow by the name of Dale Weirs, who's now I believe he's the senior technical fellow now at the Boeing company. And Dale was giving a course on gear metallurgy. And some of this information contained in this presentation is due to Dale and his efforts. But it gave me certainly the inspiration to put this talk together to say, you know, I've been around atmosphere carburizing and vacuum carburizing for some 40 years. And as a result of that, we've done just about everything everything wrong that a human being can do. So as a result of that, it might be nice to share some of this information with everybody here. But that wouldn't be possible if Dale really didn't give me the inspiration to do that. So what we're going to try to cover, and this is quite an ambitious list if anyone looks at it, is we're going to talk a little bit about cleaning. I've become very fascinated with the subject of carbides and carbide necklaces, the morphology of carbides, etc. For those that follow the Heat Treat Doctor column in December and January, you're going to learn as much as I know on the subject of carbides, so I'll be brief here. But we're going to talk about retained austenite and the fact that sometimes retained austenite is our enemy and sometimes retained austenite is our friend, and we're going to discover a little of that. We're going to talk about decarburizing and dealloying, especially occurring in atmosphere furnaces. We're going to talk about IGO and IGA and what's involved in that technology or what's involved in those situations. We're going to talk about situations with low case hardness and what some of the consequences are. We're going to talk about shallow case or no case, case leakage when we use different stop-off methods, whether they be copper plating methods, whether they be water-based stop-off, or whether they be other types of stop-off. Case core separation, case crushing. Just mention tempering briefly and talk a little about nitriding. I'd love to have included a lot more subjects. I've really whittled this presentation down, if you will, to fit in the time slot. Certainly anyone who would like a copy of this presentation can just simply send me an email and I'll arrange to get that to them. Be more than happy to. But let's start off with cleaning. And you might say, gee, this is a topic that I wouldn't have expected to talk about if I were talking about carburizing or carbonitriding. For those that do nitriding in the room, just by show of hands, cleanliness and cleaning is a major issue when it comes to nitriding. I'll say it in the form that a consultant would say it. I've made an extraordinary large amount of money by teaching people to handle things with white gloves in the nitriding world. But cleaning is certainly, and a lot of people forget this, it's the application of time, temperature, chemistry, and energy. And my definition of cleaning is to remove the contaminants from the surface to a level appropriate for the intended application. Now, a great example of this is, and how many people here deal with heat treating of fasteners? Well, a great example is the fastener industry. If you've ever approached, let's say, a mesh belt furnace where fasteners are going into the furnace for shallow case carbonitriding, for example, you're going to reach your hand down into that pile of fasteners and you're going to pull it out, and you're going to very quickly discover two things. The fasteners are soaking wet and the fasteners are oily. And what we're doing is we're actually expecting zone one of let's say a mesh belt conveyor furnace we're expecting the atmosphere in that zone to compensate for the amount of water and the amount of oil we're actually putting into that atmosphere environment. And if you're trying to put on a case depth of maybe 3 to 6 or 6 to 10 or 10 to 15 thousandths of an inch, if you stop and think about it, you'd think that having a great deal of contamination on the surface of those small fasteners would be a real problem to uniformity of carbonitriding. Well, it turns out in reality it isn't. The people in this room that do atmosphere carburizing or atmosphere carbonitriding get away with a lot of sins when it comes to doing cleaning operations. They can tolerate a high degree of dirty parts entering the system. People, on the other hand, that work in nitriding or people that work in vacuum processing, whether it be carburizing or carbonitriding or even vacuum nitriding, realize that they have to have a far greater level of cleanliness. So cleaning is extremely important, and what people think is that they can get by with 1 or 2 or 3 of these, either time or temperature or energy, and they don't need all 4 working synergistically together. Well, in reality, they do. And if the cleaning goes wrong, these are some of the consequences that you find. The picture on the left is actually something that is a green glass-like deposit that's actually growing on the surface of silicon carbide inside the furnace. I've seen this grow on silicon carbide. I've seen it grow on mullite. Interestingly enough, the insulating fire brick, typically the walls are clean, and all of the ceramics on the inside, the rest of the ceramics, are coated with a green-based glass. Interestingly enough, it's a sodium-based glass, if you ever run across this. Usually I have people call up and say, gee, the inside of my furnace is all green. And I just have a little smile on my face and go, been there, done that before. In this particular one example is the fact that the cleaning compounds or the concentration in the washer was completely out of control. And as a result of that, a lot of sodium-based, sodium phosphate cleaning compounds were introduced into the furnace along with the parts. Does anybody here do powder metal parts? Some of the lubricants that are driven off powder metal parts also produce a very similar effect. So if one day the operator comes to you or the maintenance fellows come to you and say the inside of the furnace is green, you'll know why. But once again, improper cleaning is a driving force. But no matter how bad the image on the left is, the image on the right is the real killer. These particular gears, these happen to be marine transmission gears. And these particular gears are not normally shot peened, okay? But it turns out in this particular case that due to another test that was being run, this particular company that used outside commercial heat treating services decided to shot peen these particular gears. And since I'm not going to trust the pointer, I don't know in this light, but hopefully everyone can see this area that where the peening has struck, and lo and behold, discovering that it was actually soft. This is a case of where the cleaning agents that were used and the machining compounds that were used were such that not being properly removed, the parts were then vacuum carburized, and actually we had spotty case depth on the parts. Now, what's the big deal with that? Well, heat treating doesn't often make the front page of the corporate report, okay? But when heat treating does make the front page of the corporate report, things are not good normally. Now, my one good friend who was one of the engineers here, the fellow who actually discovered this, he really enjoyed himself because he went around the world twice, going to every installation in which these gears, fortunately, had not been installed yet, and going through elaborate testing to make sure that the gears the customers had were good. And about $2.5 million later, he came home and really had a lot of fun, but it was devastating to the company from that standpoint. And of course, devastating to the commercial heat treater that was involved in this as well, because again, he had unwittingly, what he had done, he was he was vapor degreasing his parts and didn't realize that the degreasing fluid was getting contaminated by these machining fluids. So he was cleaning parts with dirty fluid. Now, because he was vapor degreasing, everyone knows that vapor degreasing is the best you can do in a vacuum environment. Well, only if the solvent is clean, right? If the solvent is dirty, we run into problems such as this. Again, normally when you see, and there's different technologies, this happens to be an example of vacuum vapor degreasing, but you need a physical action, a thermal action, and a chemical action to clean parts. What I get a kick out of on this screen up here on the right, or this picture on the right, is, you know, we've got almost a clean room environment, a fellow in a white coat and things of this nature, and just how wonderful it is. Well, I don't know if, again, with the lights on, everyone can see the picture on the right here. But this particular industrial parts washer, I'm amazed it could clean anything. In fact, if it didn't contaminate the parts, I was just flabbergasted, if you will. So many times, cleaning the cleaner, cleaning the washer, is the biggest challenge you have to producing or creating clean parts that go in for case hardening. So one of the lessons learned here is the fact that, you know, you can default to say, well, we have oil skimmers on our washers and things of this nature, and therefore the parts that are processed in the washers should be clean and dry, when in reality they're neither clean nor dry. And as I said, for those of us that are atmosphere carburizing or atmosphere carbonitriding, we can get by with a high degree of contamination on the parts. The atmosphere is very forgiving. The question is, should we get away with that? If we had to tighten up the tolerances of our case steps and things, and if you're ever dealing with very stringent case uniformity issues, cleanliness then becomes a very, very key aspect of what you want to do. So you have to be very careful with that. And hopefully this just simply makes sense, that cleaning fluids have to be dumped. You can not only just change the fluid, you have to clean the washer before you put new fluid into it. Otherwise, you've really accomplished very, very little. So this is one area that I like to point out. It's not central to the carburizing or carbonitriding process. In nitriding, of course, it's very critical, because you're not going to develop a proper case layer on the parts unless the parts are absolutely clean and absolutely dry going into a nitriding furnace. Okay, let's go on. We've covered cleaning just briefly. Let's talk about carbides and carbide necklaces. This is not normally considered something that we like to see. The photomicrograph on the left is trying to illustrate both carbides on the surface of a part. This happens to be a bearing, and also some carbide necklaces that are trying to be illustrated or shown as well. Oftentimes when we see carbides and carbide necklaces, we too often don't try to optimize the microstructure. I've become a big fan over the years that what do we do to determine in the heat treating industry that our parts are good? Normally we hardness test them, right? That's the most practical test we can do on the shop floor. But the reality is the fact that we pay little attention sometimes to the actual part microstructure. So one of the lessons that I've learned, and the simple way I like to say it is, the microstructure does not lie. That's not to imply that the people running the hardness testing are lying to you. But the idea is the fact the microstructure will give you a true picture of what's going on. Now, I have to understand that that's said from the perspective of a metallurgist. From a metallurgist's perspective, what do we want to do? We'd like to cut up every single part in the load. Now, what's wrong with that? What's that? We've got no part. Well, that's not our problem. Okay, we can tell you that every one of those parts would have been good. Okay, the problem that you have is you have no parts, but that's not, anyway. You get the message, you get the idea. But from a metallurgical perspective, when we see carbides and carbide necklaces, we realize that the carbon potential of the atmosphere was too high, there was insufficient diffusion time, the soak time was too short, these are common causes, or the hardening temperature was too low. You know, it's interesting, I look at a lot of presentations, and I'll drift off the subject for just a second, but I look at a lot of vacuum carburizing presentations and some photomicrographs that are shown, and I don't see the carbide distribution in some of the microstructures being optimized. And that says for all the good that we do with vacuum carburizing, we still have to tweak our cycles to maximize things. And similarly, you have to tweak your cycles if you're turning around and getting carbides, and worse yet, carbide necklacing. Again, you have to watch and control your carbon potential. You might have to increase your diffusion time. You might have to change both your hardening temperature and or your hardening time. One of the things about controlling carbon potential that I'll mention, especially in atmosphere furnaces, is we all rely on what device that sits in the side walls or the back walls or the roof of our atmosphere furnaces. We rely on our oxygen probes or our carbon probes, right? We rely on the fact that those carbon probes are giving us an accurate representation of what's going on inside the furnace. But how often are we either taking a 3-gas analyzer and making sure that the CO content is correct and that the oxygen probe, so to speak, is calibrated for the proper CO value? How often do we have air burnout of the probes, or how often do we make sure that that little vibratory pump, that little fish pump that's put on in an oxygen probe panel is actually functioning properly and reference air is actually going into the probe? Very, very necessary to have reference air in oxygen probes. Do we pull shims, or do we use other devices we run with the load to tell us what's going on? This is akin also to in nitriding. Many times we're obsessed with KN values, for example, or dissociation rates, depending on how we're measuring or monitoring the nitriding atmosphere. And we lose sight of the fact that we could be developing, and you'll see an illustration a little bit later, we could be developing problems in the microstructure, for example, at corners and things of this nature, if our potentials are incorrect. So instrumentation and automatic controls are nice, but we still have to monitor to make sure these types of things aren't happening. I want to go on to retained austenite and kind of walk through these in a way that we're not going to take too long. But when we deal with retained austenite, it depends on the industry in which we're involved. I mean, if you manufacture gears, you might say that, you know, having 15–20% retained austenite is sometimes advantageous because of the fact that you get a little better break-in of the transmissions and the gear trains and the power trains and things of this nature. In other areas or other industries, you turn around and, like in the bearing industry or some of the aerospace applications, you want to see retained austenite levels under 8%, under 5%, under 3%. Many times, as a matter of fact, you do, when you get into very low retained austenite levels, you start to look at X-ray diffraction techniques to determine the percent retained austenite, right? Well, you have to be very careful that the lab fully understands what's done. We had a situation where a company made linear actuators. And the linear actuators actually, because this happened to be linear actuators that helped deploy solar arrays and antenna on space vehicles. These parts happen to be tested at very, very low temperature prior to going up into space. And what was found was the fact that high levels of retained austenite were present, and these components actually grew enough to actually stop the activation or the deployment of the solar arrays and things. So we sent the parts out. Well, first of all, we got samples in the lab and we took a look at them, and at 1250X, yes, there's the presence of retained austenite. Lab comes back after X-ray diffraction and said the level of retained austenite is 38%. Okay, well, 38%, I'm at 1250X trying to find retained austenite. Okay, and you're seeing retained austenite. If it's 38%, I can just look at the part literally and see it in a macro etch almost. So you have to be very careful, and this was a good lab, but they were asked to do something and asked to look at an area that happened to be very nitrogen rich, and there was a lot of retained austenite due to nitrogen pickup and things of this nature. But if you run into retained austenite, again, you want to lean out your carburizing, lean your potential. Sometimes you want to carburize, slow cool, even subcritical anneal, reheat and quench, and certainly the almost de facto standard in the industry of solving retained austenite problems is to do some type of sub-zero treatment. I'm not going to get into the subject of whether you should deep freeze or cryo treat. That's a whole different subject. But I did sit through a presentation yesterday, and I agree with the conclusion that around a minus 100 degree Fahrenheit temperature is a very good temperature to maximize retained austenite conversion. I did find the data that maybe at minus 80 degrees Fahrenheit, all the retained austenite was not converted. Again, I don't know the situations of that particular test, but you know, the standard minus 120 temperature range for cryogenic treating will help situations of retained austenite. But retained austenite, again, depending on industry, can help you or hurt you. Let's talk a little bit about decarburizing and dealloying. One of the things that happens, and again, I'll cover this in two ways, but you can see in many parts, you can see either partial or total decarb, and the result is a lower surface hardness. It's often the way to tell it besides looking at the microstructure. You can also start to see just on the surface of the part, you can start to see some changes in the surface appearance and what appears to be more whitish appearing areas, if you will, on a part after it's been carburized. But one of the things that's interesting is not all atmospheres, when we think about them, are necessarily nitrogen methanol or endothermic gas. I ran into a situation a few years ago where my particular client was trying to actually take and carburize using nitrogen and a hydrocarbon addition. And what he was doing was the fact the atmosphere was not appropriate for the type of furnace because of the leaks, because of the drafts in this particular furnace, and he was getting significant decarb, partial and total decarb, on the surface of the parts. And we had to do things like put up physical barriers on this particular furnace to cut down on drafts. We had to smoke bomb the furnace to determine where the leaks were and fix and correct those leaks. There was a lot of work involved in that. But that's because he chose not to use an endothermic atmosphere or a nitrogen methanol atmosphere that was more forgiving. Ultimately, the solution to his problem was he did go with endothermic atmosphere. But decarburizing and dealloying can definitely be a problem. Again, there's loss of protective atmosphere. There are quite a number of box furnaces out there, either single chamber or two chamber box furnaces, where people open the door, pit furnaces as well. They open the door, what happens to the atmosphere? It's completely removed. They charge the load in, and now you'd like them to switch to high flow conditions to rapidly return that atmosphere, but in reality they don't. You can also get in trouble if the carbon potential is less than the surface carbon of the part. If you have leaks or air infiltration into the furnace, you can see problems in case hardness, you can see problems in residual stress. And again, atmosphere control, making sure your furnace is leak tight, And if necessary, depending on the type of furnace you're using, you might have to go to the extra step or the extraordinary step of copper plating or protecting the surfaces from that. How many people here use preheating of loads in air, for example? Anyone use that technique? What's the magic number that you try to stay under when you're preheating a load? If you tell me 1,500 degrees, I'll come over and strangle you. About 700 degrees, 1,000 perhaps. That's getting a little bit aggressive because you're starting to get, the rule is 700, maybe 800 degrees. You're starting to get a little aggressive and you could run into surface decarburization problems. What's the biggest the problem here, and why do I have dealloying? And I don't know that I have another slide. I do have another slide with this. One of the things that you're doing when you oxidize the surface is that you're actually, and it's very hard to see in that blue circle in there, but you're actually taking and oxidizing the chromium and molybdenum right on the surface of the part. So as a result of that, the chrome and molybdenum levels are significantly reduced by this aspect of dealloying. So, well, I call it dealloying, but it's actually oxidizing the elements on the surface. So you have to be very careful. You might have a certain grade of material that's very high in chrome and moly, only to turn around and discover, oh my gosh, I'm actually taking and destroying the surface layer due to either a preheating step in air or due to processing in a leaky furnace, for example. And we can talk about that as well. Intergranular oxidation, I'll try to just, again, you've seen other pictures of it. I don't know how the light is here. But if you're atmosphere processing, you want to look, and IGO can be very shallow, about 5/10, but can really negatively affect mechanical properties. I've got a lot of people tell me, I don't worry about IGO, I just grind afterward, get rid of it. That's one solution to it. Other people have turned to, for example, vacuum carburizing. And the latest fads in vacuum carburizing are either the use of acetylene or some type of acetylene mixtures. Well, what happens with a tank of acetylene is it's transported normally in acetone. Acetone has an oxygen-bearing element in it, so if you suck the tank dry, the last 20, 30% of the tank, you're actually bringing acetone into the furnace. It'll carburize just really well. The only problem in your vacuum furnaces, which are notoriously known for no IGO, you're going to see the presence of IGO due to the type of acetylene that's being used. So in vacuum processing, not all acetylenes are created equal, if you will, and you have to search out the ones that work best for those applications. But normally it's the result of oxygen present during atmosphere carburizing, the atmosphere control, having a tight furnace, or possibly switching to low pressure carburizing with the right hydrocarbon gas or liquid is really a solution. And it's also corrected, at least in the gear industry, by grinding to remove it. But if you're turning around, and I've seen furnaces where maybe they're going to report IGO at 7/10 versus 5/10 or something. Well, 7/10 may not seem like a lot, but you've really passed the threshold. This should be 1, 2, 3/10, maybe up to 5/10. But if you've gone more than 5/10, you have a problem in your furnace, and you should pay attention to it. So that's another lesson that's learned. Low case hardness. Once again, there can be reasons for it. Certainly, you can have the presence of retained austenite. You can also possibly decarburize the surface of the part. I mean, I've seen a lot of specifications, and I'm sure you have too, that say we want you to check, for the presence of decarb by dropping in fact, today they want Vickers as opposed to new, but drop a Vickers micro hardness reading 1/1000th of an inch from the surface, at 500 gram load. Well, it's ridiculous, right? It's like being on a springboard on a diving board at a pool, right? I get one of the grandkids out at the end of the board doesn't move. I go to the end of the board, I can just step right into the water, okay? It bends down. So as a result of this, also you have to deal, and I've had many customers and many discussions with customers that, number one, you have to use light loads when you're checking near the surface. And second of all, there's not if you're not at 500 gram load, there's no direct conversion to Rockwell C, right? The ASTM specification. So as a result of that, you get many customers that are insisting on a test that can't be performed, okay, or making a conversion that's inaccurate. So once again, the ASTM specs are your friends because they can turn around and help direct the customer to the right distance away from the surface, to use Nuke rather than Vickers in many cases, and to turn around and use the right loading and not convert it. But again, you can be carburizing too lean, you can have retained austenite, you can have a partial decarb, you can have a slack quench, can also influence the surface hardness. I didn't put loading on here, but I probably should. We talked yesterday, if you were in the Managing Distortion Conference, about loading. I won't repeat it all here, other than to make the comment that loading makes a big, big difference. So you can increase your carburizing boost time, increase your carbon potential. Again, you can carburize slow cool, subcritically anneal, reheat and quench. You can use sub-zero treatments in some cases. You're not going to correct the problem with decarburization by doing a sub-zero treatment, and you can make sure you use the correct tempering temperature.
What's slack quench?
Well, a slack quench is when the quench is not properly cooling the parts. Okay, the quench is such that it may be agitated, but it's not effectively sweeping the heat off the surface of the part. Exactly. Thank you. Let's talk briefly about shallow case or no case, and I'll try to cover these fairly quickly. But again, you see many examples in the gear industry where gear teeth are just absolutely chewed up. And the reason that when you look at them microstructurally, you realize that they have either no case or they have a problem with the case. It's extremely shallow, especially on the active flanks of the gears. A lot of times you have improper or incomplete surface preparation prior to carburizing or surface contamination. When I look at suggesting things like handling parts with white gloves, many people in the heat treat industry look at me and say, oh, come on, is that really real? Well, if you're nitriding, it's real, or it should be real. I mean, I've had clients handle gloves or handle parts with oily gloves. And as I said, this is a consultant's friend. You make a lot of money with that. But the idea is the fact that you want to very much control your cleaning. That's a very good place to look or to start to look, or possibly use low-pressure carburizing techniques to look at that. But again, low-pressure carburizing can fail as well if the cleaning is not proper, as we saw earlier. Case leakage. I'm not here to tell you that one type of stop-off material is better than another type of stop-off material. I'm not here to say that copper plating is the solution, because a bad copper plate can get you in just as much trouble as anything else. I will say that this is a significant problem. We turned around and dealt with a client, and I can't talk much about this, but they put a component into a furnace, and because the very, very deep case carburizing, and because the stop-off material partially worked and partially failed, $1.2 million later, they had to rebuild the two components that they had to scrap. So there can be devastating consequences to this. So if you're using stop-off materials, you certainly want to understand them, work with the manufacturers of them. It's more important, what's the famous Clint Eastwood line? It's more important to know your limitations than your strengths. So as a result of this, know what their limitations are. If you're using them, for example, in high humidity environments, you may have to dry the parts either with infrared, or you may have to bake them slightly. in order to fully dry. In other words, I find that sometimes customers say you must put on 2, 3, 4 coats of stop-off. So it's dip, pull up, dip, pull up, dip, pull up, dip, pull up. Gee, I put my 4 coats on and I'm ready to go, and things of this nature. So you have to be very, very careful with it. Again, you have to have good surface preparation, you have to have controlled cleaning, and many times you have to bake parts and then check the parts that you haven't blistered the surface. I can't tell you how many times that copper-plated parts in vacuum furnaces, the copper has been poorly, it's a poorly adherent copper, and the next thing you know is that the entire inside of the vacuum furnace is actually copper-plated. So you have to be very, very careful with this, irrespective if you're using atmosphere or vacuum. There are nitriding stop-offs as well. You have to be very careful with the use of nitriding stop-offs depending on the material and what you're trying to do from a nitriding standpoint. Case core separation, one of my favorite subjects, etc., is just the fact that you're going to get internal flaws and internal defects between the case and between the core, and many times you have to use ultrasonics or mag particle or fluorescent penetrant exams or things of this nature to find these subsurface cracks and things. How many people today, by the way, are using eddy current to check case depth? Anybody here? Well, if you are, just as a note, or if you're thinking about it, and eddy current does work, by the way, but what I've found is the fact that if the eddy current passes, the case is indeed good. But if the eddy current fails, the parts can still be good. That's when I get to cut up more than one, okay, and I like that. I like cutting things up. But it's a situation where the eddy current testing today can determine that the part is good, can't determine that the part is bad. So if you're thinking of that technology, keep that little insight in mind. Again, case core separation issues can take gear teeth and play tremendous havoc with them. The cracks normally occur in the substrate and then propagate into the case. So as a result of that, you have to look at the geometry of the part. This one happens to talk about gears, but look at the geometry of the part. Be concerned with carburizing too deep. You have to worry about especially corners and areas that are masked. And if you're carburizing anyway, you have to try to reduce the case depth to that. That's practical for the application. This reminds me of saying one other thing that's a pet peeve I have about one of the differences between atmosphere and vacuum carburizing. A lot of times in atmosphere carburizing, and I'm not criticizing this, I'm just making an observation, you know, we don't wait till the load is fully up to temperature and fully soaked at temperature before we start our additions gases, okay? We quote unquote save that extra time, but what we really find ourselves doing is having to have, you know, specifications of a carburized case of 40 to 60 or something like this. Huge variations throughout the load in case uniformity. I'm on a personal mission to change that. It's my own belief that, you know, we should fully soak the load before we add the additions gas. We should, as we talked about a little earlier this morning with one of the fellows here, you want to load properly, you want to control the environment to the extent you can, and you're going to avoid not only case core separation issues, but you're going to get a lot of uniformity. Case crushing follows similarly. These gear teeth are literally just torn right off the surface. Again, geometry. The other thing is carburizing too deep. I mean, almost today, without exception, I can say that probably everybody in this room has to meet CQI 9, has to perform to AMS 2750E now, as opposed to D. So as a result of that, you don't normally have a problem with temperature or temperature uniformity, but I will warn you that is often the case. You'll be very surprised by that. loading parts such that there's hot spots in the furnace, or in a vacuum situation, loading too close to the elements. Tempering furnaces or aging furnaces are not exceptions to that rule. I had a client with, would have 15 parts out of 350 parts that had property problems after aging. And I'm looking at this and I'm going, my God, it's classic overaging. What's your temperature uniformity in your oven? Plus minus 10. Well, let's survey that oven again. Oh, we just finished the survey a week ago or 2 weeks ago. Well, let's do it again. Right-hand corner had a 74-degree temperature difference. And when you're aging, that precipitation hardening stainlesses, that can be a slight problem. So never take your temperature uniformity for granted. That's another one of the lessons learned. Tempering, just ask a simple question. In a carburized part, should the tempering temperature be selected for the case, the core, or both? What do you think? The case? Anybody else? Both? Okay. Let's take a look. The case is much more sensitive, and we covered that, or there was a presentation on that talked about it yesterday. But again, the case is much more sensitive to the tempering temperature than the core. And I don't want to turn around and forget nitriding and talk a little bit about white layer. I've worked on a lot of issues with customers saying, look, I've got nitraloy 135M. And this is one of the greatest nitriding materials that was ever invented, right? It's designed for nitriding. But you have to watch, you have to watch corners, you have to watch chipping concerns. If your nitriding potentials are wrong, you start to get nitride networks in the subcase. I mean, this is almost a textbook picture, if you will. But I find it time after time after time that people with nitriding are not properly controlling their either dissociation levels or their KN factors, or they're turning around, for example, in the second stage of gas nitriding. And I want to say this in a polite way, and I'll just use the phrase ignorance, is the fact that they look at it and don't understand there was a reason why we used associated ammonia in the second stage of nitriding versus nitrogen additions during the second stage of nitriding. There's ways you can use nitrogen, and then there's other reasons for running dissociated ammonia. But if you start to look at subsurface nitride networking that outline the grain boundaries, if you will, many times you can trace that back to being out of control in the second stage of nitriding. So you have to be very, very careful with that. As I said, I couldn't cover everything in this series of presentations, but certainly, well, this is one more slide on talking about white layer and things like this, and dissociating that white layer by using two-stage nitriding, or using some of the plasma or some of the ion processing for it. As I said, I couldn't cover everything in this particular presentation, but I thought I'd leave you with these words of wisdom. The key to solving problems is really common sense. Step back from the problem. The secret is you're too close, okay? Step back from walk around the building, take a break, go to lunch, come back, think about it. But look at all the fundamental principles of what's going on. Look at your times, look at your temperatures, look at your either carbon or nitrogen potentials. Think about how the atmosphere is interacting with the parts. Is my loading proper? Is my quench proper? And certainly focus on your maintenance and think about how that furnace might be deteriorating. Think about your assumptions you make. To me, it's all about controlling not only the process variables, which we do a reasonably good job of today, but also controlling the equipment variability, okay, which is something we do maybe a little less of a job with. So I'm not here to moralize, but just make the comment that apply common sense, look at the process variables, look at the equipment variables, apply more common sense, and you'll solve most of these problems without having to hire a person like me. So thank you very, very much. We have time for two questions?
Yeah, we do
Okay.
have time.